Welcome to this second lecture. Today we cover the story of arithmetic. We have three parts. This first part A deals with the history of number systems. Arithmetic is the oldest part of mathematics. It's the science of number systems and the art of numerical manipulations of these numbers. Let's go back in time to the beginnings. In the movie The Story of One, it is explained how humans started to count with tally sticks and pebbles. The host is Terry Jones, one of the Monty Python members. He explains how humans started counting. It all began with a bone.
The Ishango bone.
The beginning of human counting has been a theme also in the movie 2001, A Space Odyssey by Stanley Kubrick. The movie features a bone thrown into the air. It then turns into a space station. It is a powerful allegory. It was the power of mathematics which gave us the intelligence which allowed us to conquer space. The oldest tally stick is the Lebombo bone. It is estimated to be 40,000 years old. Since it features 29 marks, one has guessed it has had a calendar purpose. The lunar month has 29.5 days, but it could also have been an accident. Maybe it has been appealing that 29 is a prime. Maybe the angles of these marks had a meaning. The bone had been found in the Lebombo Mountains of South Africa, Mozambique and Swaziland. It had been discovered in the 70s. Even more famous is the Ishango bone, which just had been mentioned in The Story of One. It is believed to be 20,000 years old. It had been found in the 60s in the Belgian Congo, Belgian Congo. And the numbers which appear are interesting. There are lots of primes, and the two sequence of numbers add up to 60. Someone must have been counting. In this clip of The Story of One, it is explained how the number 1 was born.
Not really.
So how did we get from tally sticks to numbers? It is an etymological riddle which can hardly ever be solved in a definite way. Here are some speculations how one can get from 5 sticks to the number 5. The Chinese tally mark arranges sticks in an increasing graph, but the etymology is often only a stretch. We see, for example, that here with our number system, even we had to cheat with 2, and after 6 it doesn't work anymore. Here's a tally code which actually was or is still used to count logs in forests. It's a beautiful system as one can just count vertices and edges of a graph. It's also known under the name Tukey tallying. The John Tukey, a mathematician hailing from New Bedford in Massachusetts. It has been used in the forest business before. Its origin goes earlier than Tukey, as there is an article of 1916 in which this counting had been mentioned. Tally sticks have not yet disappeared. They were used till the 18th century to keep track of stuff like money debts. Here are some tally sticks from the Swiss Alpine Museum in Bern. In the movie The Clan of the Bear Cave, the story of an orphan girl is told. Her name is Ayla, and she has a superior mathematical counting abilities.
Ayla.
It is essentially the mathematics which we teach toddlers. We have to move on. Here's a clip from the TV show for children, Sesame Street. It illustrates the first step of young kids have to go through when learning mathematics. In order to keep track of pebbles, one has put them into clay pockets and labeled them, but then the pebbles were not really needed anymore and clay tablets could replace them. These were the first steps of a number system. Here we see Plimpton 322. It is a clay tablet from 1800 BC. You see that it contains 2 types of marks, triangles which point to the left and triangles which point downwards. This mathematical document is one of the most famous mathematical artifacts. It features a sexagesimal system. The method of writing in this way is also called a cuneiform. It has been found in Mesopotamia. It origins in the fertile river system of the Euphrates and Tigris. It has been collected by George Arthur Plimpton, who, by the way, hails from Massachusetts. Plimpton was a publisher and philanthropist. The tablet contains a table of remarkable numbers. They describe Pythagorean triples. So here is a transcript of the numbers. To the right, the translation into the decimal system. If you look at these numbers, then one can see Pythagorean triples, like 169 square, it's 119 square plus 120 square. The 120 is missing, but one can make it up. The very left column is even more remarkable because it shows fractions and actually cosine or sine values of angles. About 2 weeks ago, a story broke about the recent paper claiming that the tablets actually contains the origin of trigonometry. It's certainly true, but it of course depends on what one calls trigonometry. If one associates it with the more modern version of cosines and sines, then this is certainly not the case. But if we just look at the sine values, then on the left, in the left column of the tablet, one really sees sine or cosine functions. Here's another tablet called Yale, from the Yale Babylonian collection 4713. Contains a collection of abstract problems. It appears that many tablets which have been found were textbooks or student notebooks or teacher notebooks. Here's a copy onto paper, and one can read here the numbers more clearly. But what are these symbols? We want to learn this. Here's another clip from the story of one which explains how the need for writing numbers might have appeared. Why did one introduce these number systems?
The other side.
And but let's move on and learn the number system. There are two types of triangles. You see the yellow one pointing to the left and the red one pointing downwards. The one which point to the downwards, these are the 1, and the yellow ones, these are the tens. So you see, for example, 10 plus 1, that's 11, or 30 plus 1, that's 31. But it's a sexagesimal system, so if one writes 1 and then afterwards 1, 2, this means 60 plus 12. So the Sumerians have used base 60, not the base 10, as we know now. So now it's your turn. Let's try to write 27. So we have the tens and the ones, and it's up to you to write this down, or 123 or 1000. We'll do that in the classroom. In a previous course, we also took time to actually draw them on clay. It's a lot of fun. You can also do that with butter, chewing gum, or whatever. If you write it in sand, you only need a stick. Here is a wonderful tablet from the Yale Babylonian collection. It's 7289. We look at it in more detail. So it contains a square with diagonal numbers attached to it. It's quite a challenge to read this. It's a bit of a clarification. You see the number 3 to the left, and then we see the numbers 1, 24, 51, 10 in the horizontal diagonal, and then we see 42, 25, 35 down. What does this mean? So it needs a little bit of ingenuity to decipher this. The number 3 actually means 0.30, which means 0.5, 30 over 60, that's 1/2. The middle number is 1 plus 24 over 60 plus 51 over 3,600 plus 10 over 60 to the power 3. And the last number is 0 plus 42 over 60 plus 25 over 3,600 plus 35 over 60 to the power 3. But what are these numbers? Here are the numerical values. Finally, we have an epiphany. This is certainly related to the length of the diagonal, the relation between these numbers. Let's go to Egypt now and read some hieroglyphs. A completely different system to write numbers. One of the most important documents there is the Rind papyrus from 1600 BC. It contains fractions, completions, linear equations, volume areas, pyramids, essentially what we teach in the first few years in mathematics. The Rind papyrus is a text, maybe can say from 5th grade. Let's learn a little bit to read the hieroglyphs. It's not a place value system, but maybe you have to put these few symbols onto a sheet of paper. Here's some mnemonic. So the priest holds a frog in his fingers, and the flower fears that the monkey is bending its stem. So these are the values. So the priest is 1,000,000, the frog is 100,000, the finger 10,000, the flower 1,000. Monkey tail is 100, the bent stem is 10, and then the other sticks like from 1 to 9. So here's some examples. It also inspired the Roman system, which is also has no... what number is this? Let's try this. So you see 2 flowers, and then 2 bent stems, and then 9 sticks. So 2,029. What number is this? We will look at this in the class. And here is another small exercise. Let's now also look briefly at the mathematics in India. It's remarkable that we have here already appearance of the 0. So this is the famous Bakshali manuscript, dated about 300 to 400 AD. It uses negative numbers and deals with arithmetic and algebra. And then also a place, kind of also independently, where 0 has appeared is in the Maya code. The Mayans had a base 20 system, so there are also dots for the numbers, and then they are the lines represent 5. So and then there is a sign for 0. Base 20, one can think it's fingers and toes. So there's a documentary about how the Maya code was cracked, and we cannot. You can look at it in the lecture. Another part of that movie about the Mayan code. Finally, let's look at the rather strange and ingenious way to represent numbers, the quipu system, which has been developed in the Andes, for example, by the Incas. So here is a quipu. The knots represent numbers written in a decimal system. So this is a decimal-based system like base 10 system like we do. And so, for example, the number 586. So you have 5 knots and then 6 knots, and 8 knots and then 6 knots. The absence of a knot means 0, so there's no actual sign for 0. Here's an overview over the mathematical documents we have looked at in this part, and this finishes the lecture. This is part B of lecture 2. We look at the real numbers. Our story starts with Pythagoras, who lived from 570 BC to around 500 BC. He had a large group of followers. They adored entire numbers, fractions, harmonies. Also in music, the picture shows them in a painting of Fyodor Bronikov. But then one of them, Hippasus, found a theorem which is astounding and troubling. It was troubling for them. The length of the diagonal of a square is not a fraction. This is called the Hippasus theorem. The proof is quite simple. It goes by contradiction. Assume the length was a fraction, p over q, then 2 is p over q, means p squared is 2q squared. Now look at the prime factorization on both sides, and especially at the factors 2. The left side has an even number of factors, while the right side has an odd number of factors. Legend tells that Hippasus had to pay with his life for the discovery, because this discovery killed the dream of a world in which integers rule. Whether legend is true, however, is not clear. Here's another proof. Might have been the proof they have found at that time. Assume we have a rational diagonal m over n, then we can scale the entire setup to have a square with diagonal m and side length n. Now place the side of the diagonal side onto the diagonal and call the rest k. So build now a perpendicular line which has length k. Now we have 2 congruent triangles, and k appears on the right hand side. This shows right hand side here, and this shows that the diagonal of a smaller square has integer length n minus k. Now we have reduced the situation to a strictly smaller square, if we do this with the smallest possible triangle, we get to a contradiction. There is another geometric proof. It's attributed to Tenenbaum. So if p squared is 2q squared, and we can just place these two squares onto the bigger square. There's some overlap and something missing. The overlap has area 2q minus p squared, and the missing parts have 2 times p minus q squared. So what we have is again written a square as a sum of as 2 times another square. And obviously these are smaller ones, so it's also a reduction argument. And this works also for other numbers. It needs some ingenuity, but this is how you would prove that the square root of 3 is irrational. And let's look at another place where irrational numbers appear. It's logarithms. Our goal is to show that the log of 2 is irrational. But first we have to review a bit about logarithms. So here are the rules. Logarithms invert the power. We take the logarithms with base 10 for simplicity here. So 10 to the log 10 is log x is x, and log of 10 to the x is x. And what is really nice, makes logarithms tick, is that the logarithm of a product is the sum of the logs. It's an important property as it reduces multiplication to addition. Logs have been introduced first by Joost Bürgi. Also, John Napier has found them independently a little bit later, but published it first. But here are some examples. So the log of 10,000, there's the log of 10,000. It's actually not true here. It's the log of 10,000 is 4. So here are some examples. The log of 10,000 is 4. The log of 1 over 100 is minus 2, because 10 to the minus 2 is 1 over 100. The log of square root of 10 is 1/2, because 10 to the 1/2 is square root of 10. Or the log of 1 over the cube root of 100, 10 to the minus 2/3. Let's just show that log of 2 is irrational. So we write log 2 is p over q. A contradiction, try to get a contradiction. We take the powers now. So 2 is 10 to the p over q, which means 2 to the q is 10 to the p. So now the left hand side is not divisible by 5. That's the contradiction. Now it's time to practice. Let's do that in class or in rooms, in groups. The square root of 5 is irrational, log 3 is irrational, and the cube root of 3 is irrational. Let's go to work. Why did we introduce real numbers? So there's one appalling reason. We need solutions to equations like x squared is equal to 2. But there are other reasons. We want to take limits. We want to, for example, compute the area of a circle of radius 1. And that requires us to approximate numbers with rational numbers and get to a limit. This is the end of part B. In this last module of lecture 2, we look at the structure of numbers. It turns out that there are many more number systems beyond the real numbers, and we have a little overview. First of all, let's start again with the integers. They can be visualized well with Cuisenaire sticks. That's how I learned the numbers in first grade, and still have my original sticks from first grade here in my office. The sticks allow to visualize rules like the commutativity of addition and multiplication. Especially multiplication is remarkable, as 6 times 5 means we take 6 sticks of length 5, and 5 times 6 means we take 5 sticks of length 6. Why are they the same? It's because of the area. Is this a proof? No, it's kind of an assumption. We take this now as an axiom for the numbers. Indeed, fundamentally, in the very small, this commutativity rule is wrong. In quantum mechanics, PQ is not QP. Then we have the fractions. So fractions are interesting and lead to some tricky math, as all students know when they learn it first. I still practice them myself. Here you see me with my personal fraction lab in January 2017. So fractions can also be visualized in various ways. Here are a few toys which have been sold for school children or adults like me. It's nice to play with fractions. The real numbers are harder to visualize. We have seen the square root of 2 before. It's the length of the diagonal of a square, but it's hard to see by staring at the diagonal why this is irrational. Indeed, every real number can be approximated arbitrarily well by rational numbers. And here we see a billiard. So the slope of the shot has been chosen irrational, which means that the ball will never return back to its origin. It produces what one calls an irrational rotation. The starting point of continuing with the number system is the problem to solve an equation like x squared plus 1 equals 0. We cannot solve this with real numbers, as the square of a non-zero number is positive, so that x squared plus 1 is positive. How can we solve this? One can introduce imaginary numbers, so complex numbers solve the problem. First introduces I, the square root of -1, and writes numbers of the form x plus iy. This can be visualized as a point in the complex plane. This plane is called the Gauss plane. Leopold Kronecker once coined the statement, God made the integers, all else is the work of man. Today you would say that the integers are the most complex numbers, and the complex numbers are the most natural numbers. The reason is that solving equations with integer solution is the hardest thing. Solving equations in a complex plane is usually very easy. There's a very common principle to build new number systems. One knows this already from the rational numbers. So a over b is actually a pair of numbers, a and b. And then you can rewrite the rules for addition and multiplications using these pairs. This is what the Egyptians did. For the complex numbers it's similar. We can just write pairs of real numbers, ab, a plus ib. And now we have just to write down the rules which give us the complex numbers. And this principle has been continued to quaternions, octonions. One has also used it to construct surreal numbers, and it's a very abstract construction of Grothendieck in more advanced mathematics. So here are the surreal numbers. It's a number system which has been introduced by John Conway quite in the 70s, 60s, 70s, and quaternions are pairs of complex numbers, and octonions are pairs of quaternions. So this pairing idea is a very general construct. Grothendieck once kind of formalized this in the most general way. If you have a monoid, if you have a construct where you can just do the multiplication, but you have no inverse, you can, in an abstract way, introduce a group. So you have also inverse. Surreal numbers introduced by Conway in 1972. It also uses the pairing idea, and it allows to define infinitely large and infinitely small numbers. It's an interesting construct. Donald Knuth has once written a book, The Surreal Numbers, or Island of Numbers, in which two are on an island and they find a stone where these rules are written in. Quaternions are very beautiful, so they are they have four components. That's why the name quaternion, and they were discovered by William Hamilton in 1843. The quaternions can be written as pairs of complex numbers. This is the plaque which commemorates the finding of Hamilton. In a flash of genius, discovered the fundamental formula for quaternion multiplication. And also number theory can be done there. One can do in the complex plane. One can look at primes. One can also look at primes in the quaternions and project them in three-dimensional space. Finally, you should probably mention the most important number, pi. It's an irrational number. I is imaginary, as is joke. Be irrational, be rational, get real. And it's used for computing area, computing volume, like the volume of a pizza. There is a very strange number, I to the I, which for strange reason is a real number again. It's known to be an irrational number. And pi itself has been computed for many, many digits. Here's the record. 22 trillion numbers have been computed in 2000 last year. Its record has been advertised in many places. The number systems, here's a little bit an overview. The natural numbers, the integers, rational numbers, algebraic numbers, real numbers, complex numbers, surreal numbers, all are included in each other. And for if any extension, there's a reason. We want to be able to solve some new type of equation. Another picture which shows the taxonomy of numbers, and we have not mentioned all of them. So we have on the top we have the natural numbers and the fractions, the rational numbers, the real and the complex, and the complex surreal numbers, and there are also algebraic numbers. P-adic numbers are a different type of real numbers, also a completion, but with respect to another valuation. The hyperreal numbers are used in non-standard analysis. The surreal numbers we have seen, complex surreal numbers are obtained from the surreal numbers, like the complex numbers are obtained from the real number. But that's it. Here are some books about numbers, and this is the end of this lecture.